Hi guys, and welcome to the 100th video on my channel. This is an insane milestone. Thank you so much for supporting me throughout all these years. And to celebrate 100 videos, I'm going to be covering a very hard geometry problem from the 2019 IMO. And this is going to be different from my typical videos because this is such a hard problem, and it's in fact one of the hardest geometry problems I've ever solved. So I'm not going to be explaining all of the motivation behind how I came up with the solution I'm presenting in the video, but rather I'm going to give some very basic motivation and go through the solution. Anyway, here's the problem. Let I be the incenter of an acute triangle ABC with AB not equal to AC. The incircle omega of ABC is tangent to the sides BC, CA, and AB at D, E, and F respectively. The line through D perpendicular to EF meets omega, the incircle, at point R. Line AR meets omega again at P. And the circumcircles of PCE and PBF meet again at Q. And what we want to prove is that DI and PQ meet on the line through A perpendicular to AI. Now, the first step in any geometry problem is, well, to draw a diagram. And the diagram is incredibly convoluted, so it's incredibly hard to draw it with a pen here. So what I'm going to be doing is I'm going to be switching over to an online graphing software, GeoGebra, and work on there. So here I've drawn the diagram in GeoGebra. And here we have the triangle ABC and the encircle DEF touching the sides. And now we have the point R such that DR is perpendicular to EF, and point P is such that AR and P are collinear and P lies on the circle. And Q is the intersection of those other two circles, and we want to show that P, Q, and DI intersect on this line through A perpendicular to AI. Now, the reason I didn't draw in the line AI is because AI is perpendicular to EF, so the line through A perpendicular to AI is just a line through A parallel to EF. Anyways, how do we even get started on this problem? Well, the first thing we want to do is understand more information about each of the new points we constructed. Now, D, E, F, and I, they're just pretty standard. Those are just the incircle touch point and the incenter. So our first interesting point really is the point R here. But if we look at the problem statement again, and you can go back to the beginning of this video if you want to look at the problem statement again. If you look at this point R, you notice that it's irrelevant to the rest of the problem. The only reason why we care about R is that it's used to define the point P. So that means that we want to understand more about P, because P is very involved in the problem, as is Q. So I'll go ahead and keep in this point R here, and if we learn enough about the point P, then I'll go ahead and delete it as needed. But for now, let's see what we can notice. Now the first step, and again, this is going to feel really unmotivated because this is an extremely hard problem, and therefore, even when I present the solution in a video, the solution might feel unmotivated. Anyways, the first key step is defining this point K here, which is the intersection of PQ with the circle. And then if we look at the segment DK here, then it intersects segment EF at this point H here. And if we look at the point H closer, it really seems like EH is equal to HF. In other words, H is the midpoint of EF. Now, before we try proving this, we might want to figure out how this may solve the problem first, because we don't want to immediately try proving it because we don't know anything about the point Q or about P on that matter. So for now, let's go ahead and take a step back and solve the following problem. So let's redefine the point K as the intersection of DH here, where H is the midpoint again, with the circle. And we wish to show that PK intersecting DI meets this line through A parallel to EF. Now I'm going to intersect this again with the circle here and call it D prime here. And now we want to show that PK and D prime meet on this line here. Now, the second key step in proving this intermediate result is to take the pole and polar dual with respect to this circle. And what do I mean by pole and polar dual? Well, the pole of a line is just, suppose that you have a line EF here, then the pole is just the intersection of these tangents here. And the pole has a different meaning when the line is outside of the circle because it doesn't have those intersection points, but it's rather similar. Anyhow, if we take the pole and polar reciprocation, we end up getting something like this. The tangents at P and K to the circle intersect at this other point here. And then we have the pole of this line through A parallel to EF is the midpoint H. And the pole of the line D prime is just this point way out there at the point of infinity. So that means that we want to show that J, H, and this point at infinity are collinear, or that JH is parallel to BC. How do we prove this? Well, given the projective nature of this problem, suppose that we ignore the point J for now. And suppose we construct a line through H parallel to BC, something like this. Then we want to show that this meets the intersection of the tangents P and K. Now this looks very, very harmonic. And what do I mean by harmonic? Well, suppose we label these points J and L here. Then if we can show that JL passes through this intersection of the tangents here, then we prove the lemma. But now we want to show that because we have these intersection of tangents here, that the cross ratio P, K, J, and L is equal to -1. And because we have the midpoint H here, this suggests that we take the harmonic bundle through the point H. So if we take PK, JK through H, J and K get sent to each other because H lies on the line. P gets sent to this point D prime. You can note that PA is like a median in the triangle PEF. And therefore, if we consider this point D prime here, because we know RD is parallel to EF, that means this must pass through the midpoint. And of course, we end up getting DK passes through the midpoint as well. So therefore, the harmonic bundle we want to prove ends up turning into D prime, J, L is equal to -1. But this should be clear because this line is parallel and therefore it's perpendicular to this line, which makes it a kite. And this ends up proving the lemma. And therefore, PK and D prime meet on the line through A perpendicular to AI. So we have basically gotten rid of the line through A perpendicular to AI from the problem. So we've reduced the problem to showing that if K is this point on the incircle here, then P, Q, and K are collinear. So how do we go about showing this? Well, we note that because we have this midpoint here, we have the point K here, and the midpoints here and the intersection of the median with the circle here doesn't work as nicely as the one with the submedian, because the one with the submedian has the property of it being harmonic, as I said earlier. So therefore, we can go ahead and try reflecting everything across the line AI so that we end up getting our submedian thing here. So let's go ahead and construct the line AI. And I'm going to go ahead and mark it in blue here so that we can see it clearly. So first, let's see what happens to the point D when we reflect it across AI. we end up getting this point x here, such that dx is parallel to EF. And these two are parallel because EF is perpendicular to AI, as I said earlier. Now we want to figure out what happens to the point R. Well, because RD is parallel to EF, as I said earlier, we know that R gets sent to D prime, because then RD is parallel to EF, which is perpendicular to AI. Then we have that the point B here gets sent to this other point B prime here, which lies on AC because we're reflecting across the angle bisector. And likewise, we have that C gets sent to this other point C prime here, which lies on the line AB. And if you do a quick angle chase, it's not very, very hard to end up showing that these 5 points B, C prime, C, B prime, and I are all concyclic. But we'll get to that later, especially the fact that Q lies on it. We'll explore this later in our proof. But for now, let's go ahead and see what happens to the point P. This point P here gets sent to this point P prime. And remember that R gets sent to D prime. So this means that P prime is an intersection of AD prime with this circle. And now we must figure out where K gets sent, because K gets sent to the reflection here. So I'll go ahead and call it K prime. And we want to see the symmedian property. And because it's a median, dk prime is just a median, so it must pass through the point A. And the points E and F get sent to each other, obviously. And finally, we must deal with the point Q. We construct this circle here, which is a reflection, because B prime P prime E is a reflection of BPS. And then likewise, we have C prime P prime F is a reflection of CEP. And that gives us our other point here, which is Q prime. And then we must show that P prime, Q prime, and K prime are collinear. Now with this rephrased problem, we can actually get rid of a bunch of the points in the diagram, including the original points P, Q, R, and K, for instance. And now we have this new problem where instead we have P prime is the intersection of AD prime with the circle, K prime is the intersection of AD with the circle, and then we have the point Q prime is the intersection of these two circles, and we want to show that P prime, Q prime, and K prime are collinear. So at first glance, this is a lot cleaner than what we originally had. But for now, let's go ahead and see what we can do. So as I said earlier, we have that these points here are concyclic, B, C prime, C, B prime, and I, and the circle also seems to pass through Q prime. Even though we're not going to prove this quite yet, it's still going to be very, very helpful for us in our proof. Anyhow, let's see what else we can determine. Because we have this point D prime here, and it's the point diametrically opposite D, we are motivated to use the fact that the angle D prime P prime D here is equal to 90 degrees. So I'll go ahead and draw that in. And if we want to use the fact that it's 90 degrees, then it would make sense if we could extend this line AD prime. And if we do, we end up getting this new point here, which I'm going to call G. Then by the diameter of the incircle configuration, we know that BD is equal to CG, or equivalently that the midpoint of DG is also the midpoint of BC. So it really seems like that point will be relevant. So if we go ahead and construct the midpoint here, then we can call this point N in what follows. Then now we have that dN is equal to NG, and this angle here is 90 degrees. But wait, that means that by Thales' theorem, dN is equal to NP, NP prime. And because dN is tangent to the circle, that means that NP should also be tangent, because they're the lengths of equal tangents. So that means that we would really expect that angle NP prime I is 90 degrees. But so is NDI. So that means that our midpoint is very, very relevant because it is the intersection of the tangents of D and P prime. Now, it doesn't seem like this point G is going to be super, super useful, other than that it constructed the point N. So we'll go ahead and delete it for now, but we'll add it back in if we need to. But for now, let's go ahead and draw in the circumcircle of the triangle DNP prime, which also passes through I. And wait, it also passes through the point Q prime. How could this be? Well, if we want to prove this, then we would need to prove that I, Q prime, N is equal to 90 degrees. And if we go back to what we said earlier about Q lying on that circle through the 5 points, then that means that we have I, Q prime, N is 90 degrees, and Q prime lies on the circle. And when we have a circle in 90 degrees, it makes sense to construct the opposite point with respect to I. So if we intersect this here, we end up getting this new point over here. And this point here, because it lies on the angle bisector and is opposite I on the circle, it has a very, very special name. This point G here, which I'm going to call I sub A, is actually known as the AX center of the triangle. And it is as special as the point I in many, many ways. So that means that we want to do something with this point IA. So now let's go ahead and do the following, motivated by our discussion above. Because the point Q prime should lie on this circle here, and also satisfy that I, Q prime, N is equal to 90 degrees, that means that Q should lie on IAN, as I said earlier. So if we construct IAN and intersect it with the circle, we should get the point Q prime. So let's go ahead and actually define the point Q prime by this definition. We will redefine Q prime as the intersection of IAN with the circumcircle of BCI. So let's go ahead and redefine Q prime as follows. It is the intersection of IAN with the circumcircle of BCI. And what we want to show here is that Q prime is actually our desired point, meaning we must show that Q prime, B prime, P, and E are all concyclic, and also show that these points here are also concyclic. And then we must show that P prime, Q prime, and Q prime are collinear, according to this definition. So now let's get started with our proof. So the first thing we must do is we note that because of how we define Q prime, we can now use the fact that this quadrilateral here is cyclic. Q prime, I, D, and P prime is cyclic with them all lying on the circle with diameter IN. And now we just need to prove that P prime, B prime, E, Q prime is cyclic. And to this end, let's go ahead and perform something called an inversion at the point I. Because we have lots of circles in the problems, it makes sense to invert. So let's go ahead and see where all the points end up. So first of all, the point B prime here gets sent to like the midpoint of XC, because B gets sent to the midpoint of DF, so it makes sense that B prime gets sent to the midpoint of XC, which I'm going to go ahead and label here. So I'll go ahead and call it here, G. And then note that G does not lie on D prime, P prime, as you can see here if I move this point A. And then the point E just gets sent to itself. The point P prime gets sent to itself, and the point Q prime, we'll have to figure out where that gets sent. Because the circumcircle of BCI gets sent to, because we're looking at B going to the midpoint of DF and C going to the midpoint of DE, we have that BC gets sent to the midline of DEF, which is also the midline of the triangle XEF. So if we construct in this other midpoint here, so midpoint here, then we should have that the point Q prime, the inverse, lies on JG. And what else do we know about Q prime? Well, as I said earlier, we know that it lies on the circle with diameter IN. So because we have ID and P prime is cyclic, we know that Q prime also, the inverse of Q prime also lies on DP. So if we intersect DP here, P prime I meant, with this line through the midpoints, then this should be our inverse. And therefore, what we want to show is that L, G, E, and P prime are all concyclic. And how do we end up showing this? Well, we know that GL here, because L and G both lie on the midline, we know that this midline here is parallel to EF, and we still haven't really used the fact that DX is parallel to EF. So LG is parallel to DX. And then there's this really, really nice property called the Reims theorem, which states that if we know that P prime E XD are concyclic and XD is parallel to LG, then P prime LEG is also cyclic. So we just need to show that P prime E XD are cyclic. But they're all cyclic because they lie on the incircle. So that immediately proves our claim. So if we go back to our diagram here, and you might notice that I've changed the position of A here, and that's so that X doesn't lie on this line Q prime IA. We now know that B prime, P prime, E, and Q prime are concyclic. And likewise, we know that C prime, P prime, Q prime, and F are all concyclic. So thus, in fact, our two definitions of Q are the same. And therefore, we can completely ignore the fact that Q prime lies on the circles, because now we know that our point Q prime is the one that we need. And finally, we must show that P prime, Q prime, and K prime are collinear, given that Q prime is the intersection of IAN with that circle. And because we have this huge circle here and we have this midpoint, we also have that K prime is also very related to a midpoint. So you want to somehow relate those two. And the way we end up doing that is by using the fact that triangle IABC is similar to triangle DEF. And the way you show this is by just figuring out all the angles individually. Because you get that all the angles are like 90 minus A over 2, 90 minus B over 2, and 90 minus C over 2. Anyways, because we have these similar triangles, we have that the point Q prime gets sent to the corresponding point in this one here. So that means that angle CIAQ prime, for instance, it is equal to the corresponding one in this triangle. And because we have a midpoint here, we know that this is angle FD, and then we have our point K here, because remember how we defined K initially. This is how the point K gets used in our problem finally. So this is equal to FDK. And because we have K prime here, we want to involve it with K prime. So we reflect it across AI again. And this gives angle EDK prime, which is also angle EDA. So now let's see what we can do with CIAQ and EDA. For one, we have CIAQ. We can try relating it to the other points. So, for example, CIAQ prime is equal to 180 degrees minus angle CB prime Q prime, which is also equal to angle EB prime Q prime. But because we have our cyclic quadrilateral EB prime P prime Q prime, this is also equal to angle E P prime Q prime. So this is very, very good news because we finally involved the line P prime Q prime. And now let's see what we can do with EDA, which is up here. So EDA. And as I said earlier, we know that this is also EDK prime. And EDK prime here is also equal to EPK prime. So this here is angle EP prime K prime. So therefore, we have deduced that E prime P prime K prime is EP prime Q prime, which means that the points P prime, Q prime, and K prime are collinear. And this is exactly what we needed, because when we go back to the original problem, we have shown that P, Q, and K are collinear. And we've shown at the beginning of the problem that P, K, and DI meet on the line through A perpendicular to AI. And therefore, we have shown that P, Q, and DI meet on the line through A perpendicular to AI, and we have solved the problem. So returning back to our whiteboard here, the main framework of our proof goes as follows. So our first step is that we eliminate the line through A perpendicular to AI by using a lemma. So in other words, we deduced a lemma that allowed us to eliminate a line from the diagram and reduce this complicated problem into one that's very slightly easier. Then the second step is to note that we have some sort of some median thing here. And with that, we have used known properties, like properties you might already know if you do a lot of geometry, to reflect across, so across AI. In other words, we get a key step. And it relates what we know to the problem. And then the third step that we did was try to find more information about the point Q prime, which is a reflection. And then we just played around to get properties about Q prime. And instead of proving those properties, we go to step 4, where we redefine point such that it satisfies properties. And then after that, we proved that the points are equivalent. By proving that the circles were concyclic by inverting. And then finally, the next last step that we did was to solve a simpler problem. Now, these first two steps here, or this first step here, is just called reducing the problem and finding out information. This one here is just relying mainly on your knowledge. This one is about trying to figure out as much as we can about the point if the problem statement is true. And then after that, these two steps here are what are called phantom points, where we intersect one thing with another and we show that the 2 points that we get are equivalent. And then finally, this last one here is just a simpler problem. And we could have just looped this process over and over again. Like step 6 could have led to another step 2, and so on and so forth. But it just so happened that step 6 finishes the problem because it was just an angle chase. Anyways, it goes without saying that this problem is incredibly hard. And I mean incredibly hard. It was, I think, one of the hardest problems on the 2019 IMO. And this is one of the hardest geometry problems that I've personally solved. And I hope that you were able to get even a bit of this video, because then that means a lot to me. So thank you so much for watching the 100th video on my channel and for supporting me throughout all these years. Please subscribe if you'd like to see more videos, and I'll see you guys in the next one.